In today's video, we're going to do a deep dive into caustics. We'll learn some of the theory behind them, why some more common techniques don't look as good as they could, how to simulate them with Blender's geometry nodes, and how to use render layers to add additional effects. If you just want to get onto using these caustics in your render, I have a pack of them on my Gumroad and Blender Market, all with 2 depth variations in 2K and 4K, fully seamless and looping, for just a few bucks. So if you'd like to help support the channel, the links are in the description. It would be greatly appreciated. Before getting to the tutorial, let's talk theory. If I have this simple water mesh made with Blender's ocean modifier, and we want to create caustics from it, how would we do so? Let's look at a simplified 2D version of the problem. In the real world, if we have the sun directly above us shining rays down at the water, when those rays collide with the water, they'll bend a little bit because they start moving slower in the water. This is what we call refraction. The angle that it bends is determined by something called Snell's law. The amount that it will bend is what we call IOR, or index of refraction. The technical definition of IOR is the speed of light in a vacuum over its speed in the given medium. For water, it's about 1.3. So, when these rays get refracted and hit the floor of whatever the water's in, it will result in some areas having an increased amount of light, shown by the rays getting closer together, and some having a decreased amount, shown by the rays getting further apart. This is basically all we need for the caustics we're going to be using today, and luckily Blender will handle most of the math for us. If I expand this back to 3D and view it from the bottom, you can already kind of see the caustics emerge from just the arrows, with areas of higher light density and areas of the opposite. So now that we know how this phenomenon happens in real life, we can get to simulating it. But first, let's look at a more common shader-based approach and explore why simulating it like we'll be doing today gives more realistic results. If we look at a reference board with a couple of images of caustics, you can see there is one thing they all have in common. They all have these areas of overlapping light that forms these really bright areas. That's in all of these, right? And then in some of them, more prevalent than others, probably most prevalent right here, you can see we have this dispersion where the wavelengths of light are actually separating. So you can see it starts here from this like kind of violet, and then it goes to red, yellow, and then green, and then to blue, and it has the same gradient on the other side. I'm not sure how well you can see that through YouTube compression, but it is there. And like I said, this just has none of that. You can maybe add some dispersion sometimes with texture approaches, but it doesn't really look the best in my opinion. If we instead duplicate this plane over and then make a new material where I'm going to make an image sequence and then navigate to my caustic texture pack. In this case, I'm going to go with basic ocean and disperse step 2, and then we'll go 2K JPEGs. And I'm just going to select them all with A and then import sequence. I'll connect the color to the surface, add a texture coordinate and mapping node with Control T, and then you can see it's just like pink. I think this is just an Eevee bug. If I enable cyclic and auto refresh and then play, it works fine. And I'm going to turn the scale down just to try and match this other one. And then I'll add a gamma node, which I think is the best way to change these. And I'll set this to like gamma 1.4 so that it matches this more closely. And as you can see, there's really no contest. This one has basically all of the features in our reference. You can see we have this overlapping light. You can really see the push and pull of the waves, and we have dispersion. If I zoom in, you can see the dispersion doesn't look that good. That's because we're just using 2K JPEGs here. If I swap it over to like 4K EXRs, you can see it looks perfectly smooth. But Eevee really doesn't like big textures, so I can't really play this. So I'll keep it to 2K JPEGs just for the sake of demonstration. This has all of the points we saw in our reference, and I think it looks great. Another benefit of the texture pack that I have is if I set the scale back to 1 and hide the other caustic, you can see if I duplicate this all the way around, that it is fully seamless and loops at 240 frames. So you can tile this as much as you want. You can have it going for as long as you want. And because it's 10 seconds long, you're not really going to see any repetition. So if you'd like to download this exact texture and quite a few more on my Gumroad and Blender Market, you can. The links are in the description. But without any further ado, let's get on to the tutorial where I show you how to make this for yourself. So to start off with in Blender, we're going to need something for our light to refract through. And luckily for us, Blender has a very simple ocean modifier. So if I just make a plane, or any mesh really, we can go to the modifier stack and add an ocean modifier. And I'll set the resolution preview to like 15 and then render like 20. We can set I want the spatial size to be like 20. So now that means that this will be 20 meters by 20 meters about. And you can play around with these settings. I'm going to keep them pretty vanilla right now. But what I am going to do is I'm going to animate the time, and I'm going to set the end time of our scene to be 240. And then at the first frame, I'll set a keyframe on time at 0. And then at the last frame, I'll set a keyframe at 10. If I play this, you'll see it's animated now, but it starts slowly and then it gets faster. And we don't really want that. So if I go into my graph editor, you can select everything and then hit T and go to linear, and that will make it so that it is a constant speed across the whole animation. And so that looks pretty good. We've got a nice ocean now. Now we need to do the refractions, and I'm going to do that on a separate object. I'll call this one Geo Nodes, and I actually forgot to name the old one. I'll call this Ocean. And in our GeoNodes object, we're going to make a new GeoNodes. We can just get rid of the group input because we're going to make a custom grid. So add a grid node, and then we'll make this size 20 meters by 20 meters so that we roughly fit our ocean. For now, I'm going to set the resolution to like 128. To raycast this, we want it to be up here, right? Because we want to shoot our rays down and then we can refract them. So we can take a transform node, and I'll just move this up by like 5 meters on the z-axis. And then we can take a raycast node pretty simply, and we can drag our ocean straight from the outliner into our geometry nodes, and then set this to relative so that if I view this, kind of looks like it disappears, but if I hide the ocean, you can now see that we have this ocean mesh in our geometry nodes tree. I'll bring the ocean back, and we can put this geometry into the target geometry. So we'll keep the ray direction at -1, and then we can set the position of our plane to be this hit position, and then that will put it at the ocean surface. And you can see we've got this like weird stretching stuff going on. That's just because if I hide this and go into top view, you can see in some areas our plane is actually over the bounds of our ocean, right? This is where our ocean ends, and these vertices are over it. So if we shoot rays down, we're not going to hit anything, which means this hit position will be 0. So in those areas, I'm just going to delete it. So we can take a delete geometry, and then this is hit value shows us where it is hit. So you can see here, it's not being hit, and that's what's causing the stretching. So if we invert this is hit value by taking a Boolean math set to not, now we have the inverse of that. So this is only what is not being hit, and then we can plug that into the delete geometry, and that gets rid of it. And so now we have none of that gross stretching, and I can hide our ocean for now. Now we have this plane with the ocean, or at the same position as the ocean basically. And the reason that we do that instead of just using the ocean directly is if I view this in wireframe, you can see on the ocean, everything is moving on the X and Y quite a bit. It's moving all over the place. But if I just view our geometry nodes tree from the top view, it doesn't actually look like it's changing. It's only changing on the z-axis, which is exactly what we want for this. And so I'm just going to frame this up. We'll call it sun raycast. And so now we need to do the refraction through our water, right? We've cast rays down from the sun. Now we need to refract them. And how are we going to do that? Well, Blender has a very handy node, vector math, and it even has a refract option. And so this has 3 inputs. The first vector is our incident vector, or I. The second vector is our normal vector, or N. And then this IOR is not what you would expect it to be. You might remember that I said the IOR of water is 1.3. It's actually like 1.3 repeating, but it doesn't say it on the node, like if you hover over it, which I think is kind of dumb. I think it should say this, but this is actually the IOR of medium 1, so I'll just call it M1, over the IOR of medium 2. So what does that mean? If we're here going from air up here to water down here, this would be the IOR of air over the IOR of water. So when I'm using this refract node, I actually like to take a math node set to divide, and then I can just plug the 2 separate IORs in there. So in this case, the IOR of air would be about 1, and then the IOR of water would be about 1.3. And so this is going to come out to be about 0.75. And back to these vectors, the incident vector, that's just going to be our ray direction that we used back here. That's basically what vector do our light rays hit the surface with. And then the normal vector is the normal of the surface. So in this case, it's the normal of our ocean. But since we set the position of our grid to the ocean, that's the same thing. We can just use the normal of our grid. We have our incident vector, which will be -1. We have our normal vector, which is just the normal of our mesh. And then the IOR, which we already said was this. So this is actually all we need for the refraction. If we plug in another raycast with, let's just make a grid. And if I view this, we can see it. We'll make this grid go down on the y-axis, or on the z-axis, by like 5, and we'll just make it like 100 meters big. Doesn't really matter. And then we can plug this transform geometry into the target geometry and this vector into our ray direction. So now what we're doing is we're refracting it. So let's say this ray gets refracted here, and then we're going down until we hit this plane. And once we hit this plane, we're stopping there and saying, okay, that's where our light lands on the floor of the ocean. So if I take another set position, plug this hit position into the position, now you can see, if I get rid of all these annotations and I go into top view, we already have our caustics coming up. One thing that I find helpful is you can see just how like jagged this mesh is. I like to blur the normals just a bit. So in this case, we'll do a blur attribute set to vector by like 1 iteration. And you can see that really helps. If I mute it and unmute it, that really helps define our caustics in a smoother fashion. So yeah, that looks great, I think. Already we're getting really nice results. So now let's get to actually rendering our caustics, because right now you can't really render this, right? It's just a wireframe. So the first thing that I want to do is I want the areas of higher light density to be displaced up. But how do we actually find out what our light density is? We can take the face area, right? If I mute this, you can see all of these faces have the same area. But if I unmute this, now these faces have grown, right? They're a lot bigger than they were before. And these faces have shrunk, like these ones down here. These ones are a lot smaller than they were before. So the pattern here is that In areas where there's less light, the faces grow, and areas where there's more light, where stuff is overlapping, they shrink. So what we can do is we can take the face area, and I'll store it back here, make a store named attribute, store the face area, and I like to square root it, just because you can see here, it's kind of hard to like see what's happening, but if I square root it, it's a lot brighter. You don't have to do that, but if you don't, you'll have to adjust a bit of the math. So we'll call this face A, and I think I'm actually doing this in the wrong place. You want to do this before the sun raycast. So I'll move this back here. And then now, after this group, which we'll call the water raycast, we can copy this whole store named attribute, and in this case, we'll name it face A N for face area new. If I make a named attribute node and view the face area new, you can see that it is black where the light is more concentrated, and it's white where it's less concentrated. So if we just subtract this from 1, which is a fast way to like invert, and then we can set the position of this with a combine XYZ. We'll set this into the Z and then this into the offset. Now we can see our caustics in the viewport already, right? Because we're offsetting the area based on their light. But how do we actually like determine how bright it should be in the render? In that case, we can take our old face area, in this case just face A, and then our new face area new, and then we can subtract the new face area from our old face area. You can already kind of see that we're getting what we want. I find you get better results when you multiply the new face area by a small value, like 0.2. That looks pretty good, but it's very low contrast, right? So what I'm going to do is I'm going to make 2 math nodes, one set to multiply and one set to power. And then we can multiply this by like 10 and set it to the power of 8, and then just turn this multiply down. And now we're getting that nice contrast. So yeah, this looks really good. We're getting our caustics, the overlapping light you can see, and the areas of lower light. And if I unhide our ocean, this is directly related to what's happening up there. I mean, obviously, but it's kind of cool to watch, I think. You can really see where there's waves, the light's getting concentrated down. Up here, there's a wave. Then down here, the light's getting concentrated. And up here, there's like a flat area. So down there, there's less light, right? I think it's really cool to just, watch. You can see it's pretty low resolution right now. We can fix that by just turning the resolution up. So I'll set this to like 256. That does mean that you'll have to change this. I like to change it back here. So we'll change this multiply. I doubled the resolution, so I'll double the multiply as well. And then I'll also have to double the blur attribute. You can set up controls for that. And I actually think I want to turn it up even more. Yeah, that looks good. And so now we can just store this as a new attribute, and we'll call this caustic strength, plug this power into there, and then we'll make a set material node, and we'll make a new material, call this caustics, set that to that material, and then we can just use this attribute directly in the shader by using an attribute node and calling it the same thing we call it down here, and then plug this into an emission shader, plug that into the surface. By going to rendered view, we have our caustics. Very nice. And so if you want to render this, I recommend using an orthographic camera. So I'll just make a camera, reset its rotation, and then set it to orthographic, and we can make the scale 20, and then that will mean we're viewing a 20 meter area, and I'm actually going to want to set this to be 1080 by 1080, just so that we're viewing that entire square. And I think I'm actually going to turn this down, just so we don't see the edges. Very nice. And we can render this in Eevee, we don't need to use cycles, and I'll turn the passpar 2 of our camera up so that we're only seeing what's in camera view. We don't need shadows, we don't need temporal wave projection, we don't need motion blur, none of that. And we'll use the standard view transform for this with no look. And that looks pretty good. So I think this looks good enough to render. If I do that, I think I want to turn this resolution up even more, which of course means I'm going to need to change these values. And then if I just render this now, I forgot to hide my ocean in render. We need to click that button over there to hide it in the render. And then now if I render, we'll just be seeing our caustics, but we don't have any dispersion, right? And that's a really cool effect, I think. So I'll show you how to add it, and we're actually going to use render layers to do that. If you've never used them, don't worry, it's not hard, especially in this case. So what we need to do first is let's move our geometry nodes object into a new collection. So I'll just do that by hitting M, new collection, and we'll call this caustic 1. I'm going to disable this in this view layer. And if you don't see that option, you can go up here into the restriction toggles and turn this off or on, the exclude from view layer option. So I'm going to exclude that from this view layer just for now. And then I'll right click on the collection, duplicate it once, hide it, duplicate it again, hide it. And so I'll just view this one, and we'll name the other collections caustic 2 and then caustic 3. And for this, in this geometry nodes tree, we're going to need to make a couple group inputs because we want to be able to control the IOR outside. So I'll put this here, put that there, and then I'll call this top one IOR air, and then I'll call the bottom one IOR water. So now you can see those are in our modifier stack. And now on this caustic 1, I'm going to leave that alone, so I'll hide it. And then on caustic 2, I'm going to change the IOR of water to be, I don't know, we'll just go 1.2 and then 3 repeating, and then we can hide that. And then in caustic 3, we can go 1.4 repeating. Or 1.43 repeating. And then this is going to be a pretty strong caustic or dispersion effect, but I just want to show you for now. So with all of that set up, what we can do is up in our view layer up here, we can go press this button to add a new view layer and then do copy settings, and we'll do that twice. And so now if I click on this, you see we have 3 view layers. For this first one, I'll call it caustic 1 and set this first caustic to be enabled. For the second one, I'll call it caustic 2 and then disable this first one and enable the second one. And then in the third view layer, I'll call it caustic 3 and do the same. Disable the third one, or disable the first one and enable the third. And so now when we go to render, you see it renders all 3 of those, right? So now we have these 3 view layers up here, caustic 1, caustic 2, caustic 3. So now in the compositor, in our render layers, we can duplicate this 3 times. Caustic 1, change this one to 2, and then change this one to 3. And if I just combine color, plug this into R, this into G, this into B, and then plug that into the composite, we have dispersion. And like I said, this is really strong. Turning it up really high is nice to be able to see what you're doing, and then you can turn it down later. So this is not what I want. I want it to go red, then blue, then green, like it showed in our reference. Yeah, so red, green, blue. So currently we're going green, red, blue. So if I should just be able to switch these and then switch these, and right there we go. That's what I want. So I'll plug caustic 3 into red, caustic 1 into green, and caustic 2 into blue. And then that is our dispersion. And so I'm gonna go back now and change these values. So for this one, I'll go like 1.3 plus 0.05, hide it, and then unhide the other one so I can mess with it. I'll go 1.3 minus 0.05. And you can automate all of this obviously if you want. And then now if I go to render, it'll render all 3 of them and it will composite them together. Actually, I might have messed this up. Oh yeah, oops. Okay. I actually had them in the wrong order there. This is still pretty strong dispersion, but just for the sake of you being able to see it on YouTube. So this is basically all you need to do. Now you can render this out as an animation and use it in your own renders if you'd like. This won't be seamless and this won't be looping currently. You also might still see some of those square artifacts if you render at higher resolutions, which can be tricky to fix. All of those are fixed in my product on my Blender Market and Gumroad. So this looks pretty good. You could stop here and be done with it. But there's a lot we can optimize in this geometry nodes tree. If I go back to my nodes, we can do a lot here. If you don't care that much about this optimization, you can skip this, but I think it's useful. So I'm just going to actually duplicate this whole thing and move it down just so that we have this up here to reference if we need. And the first thing that I'm going to do, delete the sun raycast. We don't need it. It's useful to think about it like that, but we don't actually need it. Next up, the water raycast. We're also deleting this. Delete this set position, delete this transform, and this grid. We don't need any of that either. What we can do instead of raycasting onto something, or onto like an infinite grid, we can do that with math, and we can raycast onto we'll bring the ocean back in, set this to relative, plug the geometry into the target geometry, the ray direction to -1, and then we can use this hit normal as the attribute on our refract. So if I view this hit normal, you can see this is the normal of our ocean. And I'm gonna move our camera up just so we can actually see this when we go to render it. But yeah, this is the normal of our ocean, and then we go ahead and blur it, and then we refract. Now I'm just going to hide unused sockets on this raycast so that it's a little more condensed. What I'm going to do is I'm going to normalize this refract just in case to keep its length to 1. And then we can scale this down. And if I just set this position, plug this into the offset, then I'll view it from my camera. You can see the more we turn this up, the more strong our caustics are. And this is actually what the depth parameter is on my texture pack. Depth 1 is a value of 3, and then depth 2 is a value of 6. But this obviously still doesn't look very good. We have a lot of clipping. And that's because if we go into 3D view, if we view this from the side, you can see that it's not flat, which is not what we want, right? We want it to be flat. And you could raycast for it. That's what we were doing before up here, right? If I view this is perfectly flat after the raycast, but this isn't because we're not raycasting, right? We can project this onto a plane with vector math. And the way that you do that is you take a vector math add, and we add our position to this. So this is the refracted position. If I set this into position, we get this. And then we want to project this, vector math project, with the normal of whatever plane we're projecting onto. So in this case, that would be 1. And then we need to subtract this project from our original vector. So if we subtract this From that, we get the projection, and it is now a flat plane. Beautiful. So now if we view this from rendered mode, we no longer have that clipping. If I mute this, clipping, unmute it, no clipping. Beautiful. Yeah. If I turn on timings, you can see our original version is taking 102 milliseconds to calculate. And if I plug in our new one, it's taking half the time. I think on average, yeah, it's like 74 milliseconds. So like 3/4 of the time. But yeah, it is substantially faster. Or like, why, right? Why do these nodes give you the projection of this vector onto a plane, right? Let's think about it from 2D. If we have a plane here and a vector like this, we'll call this V, and it will equal 3, 4, let's say. And then we have the normal vector. We'll call this N, and that will be 0, 1, right? It's just pointing straight up. If we take the projection of V onto N, I'll switch colors for this, that would be this arrow, right? Because we're just projecting this onto N. So this projection, we'll just call this proj, well, it'll be projection of N, the projection of V onto N, which is, that's how you write that. This would equal 0, 4. And so now, if we want to get this vector's position on this plane, all we have to do is subtract this from this, right? We take our vector, which is 3, 4, and we subtract our projection, which is 0, 4, and then we get, I'll make a new color, make this green, we get 3, 0. And so this is the position on the plane, which would be this, right? Because we're just subtracting this vector from this vector, and that would be going down here. Because this is just the distance on the y, or on the z-axis. In this case, it's y because it's 2D. And so that would put us right here, because we're just basically negating this y, right? And we're just left with this. And this works in 3D as well, and on any axis. So that is why this vector math results in its projection on a plane. And if you don't feel like you understand any of this vector math, don't worry. I have a video, a very big video that I've been working on for months, where I explain every single operation in the vector math node, from add all the way up to refract. We're going to go over all of the insides of every single node and why they do what they do, some practical examples, and the true math behind them, like here, but in a more structured way. So that's it for the tutorial. Now I want to show you how you can use these caustics in your own renders. So whether you decided to download my version on my Gumroad and Blender Market, or if you wanted to export your own, like I showed you in the tutorial, I'm going to be using the ones from my texture pack. And if you want to download the texture pack, what you're going to be greeted with is a lot of these tiny zips. Basically, all you have to do to extract these is click on this main ocean.zip, and then with like WinRAR or 7-zip, you can extract it, and it'll extract all of these. But onto the use. All you have to do is make your scene. So I'm just going to do something simple here with like a plane and a monkey. And then I'll make a spotlight. This works with both spot and area lights. I prefer spotlights. So I'm just going to backlight this monkey here. And then with the light selected in the shader editor, you can hit use nodes, and then you can actually do whatever you want, like what you normally do in normal shader nodes in here. So we can just make an image sequence, and then I'll navigate to my true caustics folder, and I'll use directional waves, disperse depth 1. And then we can do 2K JPEGs, should be fine. Import image sequence, and then enable cyclic and auto refresh, plug that into the emission color. And then if I just go into rendered mode and turn my world shader strength to 0, and then I can just right click and adjust light power to turn this up, we have our beautiful caustics. And if I play this, it's pretty slow because, you know, cycles. But you can see we have the directional waves going, and it looks pretty good. I think I want to increase the contrast a little bit, so I'll do that with a gamma node. But yeah, that looks sweet. And I'm going to scale this plane up even more so we don't have that cutting off. If I just make a cube and scale this to the size of my scene, and then I'll hit Control A and apply its scale, we can make a new material on it and just delete this BSDF. We don't need it. We're going to do volume. So I'll make a principled volume, plug it into the volume, and then just turn the density down. And now if I go here and just turn this light power up even more, you can see we're getting those really nice light beams coming through. And you can obviously get way more complex with the shader. This is like the simplest you can be. Even with this simple shader and this gobo on the light, you get these beautiful light rays that correspond with your caustics. And yeah, I think it looks pretty sweet. So that's all you need to do to use these textures in your own renders. If you want to be using these caustics in Eevee, you're not going to be able to use any of the textures really. You can't use texture projection on lights like you can in cycles. So instead, what I've done is I've made a workaround. It's not the greatest. I still probably wouldn't recommend really using this in Eevee, but I mean, you can, as you can see here, this is Eevee, and we have some caustics going. As you can tell by my frame rate, it is very slow, and this is at a really low resolution with no dispersion. If I turn dispersion on, going at 2 frames per second. But it does look quite nice. So if you want to use this in Eevee, all you have to do is, this is marked as an asset, so you can put this in one of your asset library folders, and then use this geometry nodes tree in any of your projects. And I'll walk you through the settings real quick. The water object is just whatever you want stuff to be refracting through. So in this case, it would be the ocean. The colliders are obviously just whatever you want your caustics to collide with. So in this case, I have the monkey, cube, ball, and this container all in one collection, and then that's there. And the direction method is how you want your caustics to be pointed. So in this case, I have sun object, and that's because I have a sun, and I can move it around, and the caustics will follow it. But if you want to, you can also switch this to vector, and then you can just control this with a simple vector input. So it's up to you, whatever you want to do. I like using sun object in this case. The resolution and size are the same as the other blend files in True Caustics. Pretty self-explanatory. And then onto the refraction settings. This strength is kind of like an ocean depth parameter. They get pretty wonky when you put it higher. And then the IOR is the same as what I showed in the video. Pretty self-explanatory. And then the dispersion is actually here instead of render layers. You turn that on and we have dispersion right in the viewport. But this is 3 times slower, or about 3 times slower than without dispersion, because you actually have to calculate it 3 times. But it's really the only way to do it as far as I know in Eevee. So you can also change the strength of dispersion right here. So yeah, if you want to use this in Eevee, that's basically what you have to do. I don't think there's really a workaround. In Legacy Eevee, you could have used them as gobos, but you can't really do that in the Eevee Next. It's just really noisy. So this is, I think, the best way to do it in Eevee. But like I said, I still wouldn't recommend it, but I wanted to give you guys the option in case you did want to do it. But it's pretty laggy, so be warned.